he says you can define the smallest equivalence relation on X, having A as an equivalence class, is as follows. Check this out. So X is equivalent to Y, all right? What?
Only if X equals Y or X and Y are both in A.
Right, X is equal to Y, or X and Y are an element of A. So what that's saying is that this equivalence class leaves points alone. It says the point is equivalent to itself. All right? Unless it's in A, in which case they're all at the same point. So what this does is it's like squishing the whole subset A down to like one point. That's what's happening with this mapping. The fibers are all singletons, except for this one, which is the n-1 sphere cross 0. So that's a way to look at this n sphere. It's the quotient of that and that. It's another way we could look at the n sphere. Okay. All right, next example is nice. I like this example. The hypercube, example 511. The hypercube is what? It is In, which is the unit interval 0 to 1, Cartesian product n full times. This is a subset, of course, of Rn. Right? He says, contract its boundary, all right, to a point. Now he says do you understand? He says the boundary of In is, he's using this French notation, so maybe Daniel can explain it to me. 0, 1. It seems to me, oh, I see what he's saying. Oh, duh. He's removing the open interval from 0, of course. Yeah, of course that's the boundary. That's just the set of points that have either x,
That French notation.
either x equals to 0,
Yeah.
or y. Well,
Like any coordinate equal to 0 or 1.
yes. I shouldn't say x and y. There are a lot more coordinates than that, right? There's x1 through xn. All right. Then what? Contract its boundary to a point. So what he's saying is, let this be the A in this construction over here. This, and then form an equivalence on In by just saying In mod, that boundary. Then what do you have? He says it's homeomorphic to the n sphere. All right. This is homeomorphic to the n sphere. Why? He says because In, all right, is homeomorphic to Dn, right? How do you get from something else going on here? And we saw in example 5.7, oh, there's the 5.7, that there's an identification dn to Sn contracting the ball's boundary to a point. let's see here, fine. 5.7 was, we had F, a mapping from Dn to Sn, right? And the formula, of course, was, we remember we had remarked that the boundary, F of the boundary of Dn was what? 0, 1. So that means that the inverse image of the set containing 0, 1, which is, this is a point, is the boundary. Let's try it again, it goes upstairs. Try to put it together here. So what's that say? That says, oh, is that it for the 5.7 map? He says its restriction's a homeomorphism. So in fact, the F map, which I wrote the formula for before, we found the surjection. It's 1-to-1 if you ignore the boundary. It's many to 1 on the boundary. Many to 1 on the boundary, but setting aside the boundary of Dn, like F restricted to the interior of Dn, right, is 1-to-1. So that means if you look at the inverse image of Sn, anything in Sn, let me just call it Z, it's a single point. Single point in the interior of Dn, as long as Z is not equal to 0, 1. So like the whole boundary of the n disk is contracted, squished to the point 0, 1. And then everything else is just left on its lonesome. Is there a correction?
No, I'm just saying it. So the reason we're using Dn is because it's homeomorphic to In.
Mm-hmm.
So it's like the argument is kind of the same. It's like the boundary of In will be contracted to a point as well.
Yeah, I
when
think.
you like combine the two mappings.
Right. So I mean, what does the F bar give? The F bar here is what? F bar is the mapping from the quotient. What? It's using the fiber equivalence of the map F. It's a mapping from Dn mod the fiber equivalence, right? Of F. So that maps onto what? Sn, right? And that's a homeomorphism. And homeomorphisms map boundaries to boundaries, I think. So.
It's 5:05 p.m.
Curses. Can we go a little bit late today?
Not too late. Like no later than 5:15.
Okay, I'll talk faster. I gotta think faster though. That's the real problem. Talking I can do. Thinking is the hard part. So that's a homeomorphism. So yeah, I mean, you said when you say Dn.
It's homeomorphic to In.
Dn is homeomorphic to In. Right. So
So the boundaries are homeomorphic. Or can you say that?
yeah, I'm trying to see how he gets. I mean, how does he get from this to that? Do you understand that?
So he goes through the intermediary of dn. I think that is equivalent to saying that like dn mod boundary of dn is homeomorphic to Sn. Which
Oh. So the argument is, it actually is this.
It's
So you're saying it's just this is homeomorphic to dn, mod the boundary of dn,
which is homeomorphic to Sn.
which is homeomorphic to Sn by example 5.7, yeah. This, well. Okay, and that has nothing to do with this.
No.
Okay. I was originally trying to make this part of the
Oh,
story,
yeah.
which is just nuts.
Yeah.
That's just the previous example. Why didn't I erase it? So it can't harm me. Stupid. Ha! Dead. Die. So we have a couple different ideas going on, right? Like, given an abstract equivalence of a topological space, we can form the quotient space, right? Which makes the equivalence classes the natural image of the projection map, and that makes the projection map an identification from the given topological space to the set of equivalence classes, right? And then we have this other idea, which is if we have a continuous mapping, we can form the fiber equivalence. And then the quotient by that fiber equivalence will basically take the fibers of the map and squash them to be like points in the quotient topology. These ideas are overlapping. Okay, so where was I? He says the Mobius strip can be physically constructed by taking a rectangular strip of flexible material such as paper, leather, thin plate, etc., gluing two opposite sides after twisting one. So usually you draw a picture or something like this, right? So I think that's pretty much
The matching of the arrows.
right. And you have to.
Oh, that's the drawings like they had in the beginning of the book.
Yeah.
Now here's what he says. If you want to be constructive about it, you can take the closed set 0, 1 cross 0, 1. Right? That's a subset of R2. And what's the equivalence that you... I mean, what this is really saying, so if you think of this as being... Sorry, let me make it a little more squarey. So what is this saying? If I put this one at 0, what's that?
You did the wrong direction.
That's something else. Just a cylinder, I think. But anyway,
What does it say?
so what do you have? You've got, if I've got the point like x, y, where 0 is less than x is less than 1, right? Then x, y is equivalent to x, y. That's it. If on the other hand x is equal to 0, right, then, well, I mean, we can just be more descriptive. 0, 0y is equivalent to 1, 1 minus y. So for example, 0, 1 is equivalent to 1, 0, and 0, 0 is equivalent to 1, 1. So that's this we can think of as x, right? That defines an equivalence relation. And then x mod this equivalence is essentially the Mobius strip. And he's like, then you can think about the Klein bottle I won't try to visualize that, that one. All right. He says the quotient space of a compact space is compact, and the quotient of a connected space is connected. This is not true for Hausdorff spaces, though, because you can have the quotient of a Hausdorff space, which is no longer Hausdorff. That is an annoying but true thing. I wanted to prove Theorem 5.14, but I don't think we have time. Curses. Well, it's at least 5. Because that cursed woman said something to me a minute ago.
5:05.
Okay, so well, I guess we can give it a shot. I mean, that's the end of this section at least, right? At this rate, we'll never be out of this chapter. That's okay, though. I do think this material is harder, and it's important to understand it. Theorem. Let f from x to y be an identification, x compact, and Hausdorff. All right. That's it? That's it. The following are equivalent. Numero uno. Y is Hausdorff. Two. F is a closed identification. Three. Ooh. K equals to x1, x2, an element of the Cartesian product of x and x. All right. Such that f of x1 equals to f of x2 is closed in the product. This is Theorem 5.14. He seems to say that the quotient of a compact space and the quotient of a connected space are connected rather glibly and in passing. Can we understand those? I mean, the proof is in the book for this one. He doesn't really explain why it is that the quotient of a compact is still compact. Think about that for a second. If you have a quotient space, right? If you have x, and so there's a projection, right? The projection's an identification onto this, right? If this is compact, what's that mean?
It's the open covering of the final subcover.
Okay. So if we take an open cover of this, right?
All of those are images of every open subnet is an image of an open sub and X.
So since pi is an identification, and we have open sets in the range, in the codomain, It must mean that they're the images of open sets.
Yeah, doesn't it also just come from the fact that pi is continuous? Which is that the image of a compact set is also compact.
Right.
Yeah.
Image of a compact set. Oh, right. That's easier. I don't have to think through it. Good. How about connected? Oh,
Yeah.
okay, so the fact that pi is continuous means duh. Okay, yes, so of course x is compact. The quotient is the continuous image. I mean, the quotient topology is essentially constructed as to make pi continuous. Right? It makes pi an identification. It makes pi. So this is the finest topology on the quotient, which makes pi continuous. Those things are starting to make more sense as we talk longer about them, right? This is more of a dark magic, though, isn't it? All right. Do you want to pick one of these implications to prove? And we'll call it a day? Or is it too late already?
Well, I think 1 to 2 would be pretty quick.
1 to 2? Aha. So why is that?
Because x is compact and y is Hausdorff.
So if y is Hausdorff, x is compact, that means so f is closed. Okay, we got that one. I think we have time for one more. Hence f is closed. Okay. Now, wait a minute. But don't I need it as a surjection as well, or?
It's an identification, so it's a surjection.
Oh, am I also given that f is an identification?
Yeah.
That's important. I should probably break that out. Yeah, if we don't have that, then we're kind of stuck there, aren't we? Because you can't. I don't think you automatically get.
Right.
You don't automatically get surjection from that data. You need surjection from this, and then. Okay, closed surjection, so it is closed. Therefore closed identification. Okay. Then what? You want to try for 2 implies 3?
Sure.
So we assume f is a closed identification. I'm such an idiot. I was reading this as part of the theorem.
Yeah.
Doofus. All right. So we need to look at this. So you want to look at the complement of that, right? I guess. So what's x? What's now? I know it's Hausdorff, right? X being Hausdorff tells me stuff about the diagonal. Yeah, I'm going to have to think harder about that one. He does 3 implies 2. And then he does 2 implies 1.
The opposite direction.
And then he does 1 implies 3. Okay. We'll come back to this next time, probably. Let me just tell you guys where we're going. Basically, you're going to see how we use this quotient construction to construct new spaces. Probably the most important one of those is the projective spaces, where the equivalence, you take, I think you take basically points along a line and view them as equivalent. So another way of saying that is your points are lines.
Mm-hmm.
So that's projective space. The topology there is really given to us by this quotient topology. But anyway, we'll keep talking about it eventually. It'll make more sense. And I will email you guys later today your homework. Because I still owe you the next batch. And I will try to actually look at your solutions.